Hello, welcome to Compton Effect, lesson for Physics 30. Now, when we talk about the Compton Effect, the main thing here is that we've got an electron that is scattering. So we've got an X-ray usually, an X-ray photon coming in. So that's an X-ray. It's coming in and it deflects off at some sort of angle here, giving an electron some momentum. Now, that electron now has more energy, which means that the electromagnetic radiation has less energy. Here's a key thing though. Both energy and momentum are actually conserved in this process. And so what that means is that the X-ray must have momentum. So key takeaway here, if we see this is the Compton effect here, you've got that X-ray coming in, hits the electron comes off, and the X-ray moves. So key takeaway, first of all, photons have momentum. Even though they're massless, they have momentum. Our traditional momentum formula, P is equal to mv, it's massless, yet it has momentum. And when it collides with the electrons, energy is also conserved. It's an elastic collision, meaning the kinetic energy before and the kinetic energy after is going to be the same in both cases. Now, the Compton effect was first observed by Arthur Compton in 1923, and this discovery led to his award of the 1927 Nobel Prize in Physics. The discovery is important because it demonstrates that light cannot be explained purely as a wave phenomenon. His work convinced the scientific community that light can behave as a stream of particles, aka photons, as Einstein had first hypothesized with the photoelectric effect, whose energy is proportional to this frequency as discussed by Max Planck in this formula. So Compton tied Planck's hypothesis with Einstein's suggestion of the photon and kind of put it all together. We've got three formulas that deal specifically with this idea of the momentum of an electron. Momentum of a photon. First one here, momentum is equal to Planck's constant divided by the wavelength. Second one, the energy of a photon is equal to its momentum multiplied by the speed of light. And the third one, as this photon comes in here and switch, it's going to change its wavelength. Obviously, as it changes momentum, as we've got a momentum collision here, its wavelength will change and it can be detected, calculated using this formula. So example number one, what is the momentum of a photon with a wavelength of 625 nanometers? Well, as we've just talked about on the last page, P is equal to h over wavelength. And so the wavelength is equal to h over P. Oh wait, we want just the momentum. 6.63 times 10 to the negative 34 joule seconds over 6.25 times 10 to the negative 7 meters. And that gets you a momentum of 1.06 times 10 to the negative 27 joule seconds per meter. Now let's discuss this units for a bit here. A joule, if we remember that work is equal to the change in energy, that means that force times distance is equal to the change in energy as well. Units for force is meters, force is newtons, Displacement is meters, and so a Newton meter is equal to a joule. Now, if we replace joule seconds per meter, if we replace the joules with Newton meters, so you wind up with Newton meters seconds per meter, notice the meters cancel out, and you're left with Newton seconds. A Newton, if we remember correctly, that idea of force, because F is equal to ma, a Newton is equal to a kilogram meter per second squared. So if we replace the Newton with a kilogram meter per second squared multiplied by seconds, those cancel out, and you're left with kilogram meters per second. So the joule seconds per meter is the same as a Newton second, which is the same as a kilogram meter per second. Remembering our impulse formula, force delta T is equal to m delta V. Force has standard units of newtons, time seconds, mass kilograms, and velocity meters per second. All three of these units are correct units of momentum. It's one of the reasons why we keep to standard units with this, is so that we can make those conversions rather easy, such as within example number 2. We've been given the momentum in kilogram meters per second, and we're looking for the frequency of the electromagnetic radiation. We know P is equal to h over wavelength, or the wavelength is equal to h over P. What we're going to use here is our standard units for Planck's constant. And keeping momentum also in standard units automatically means that the wavelength is going to also be in standard units of 2.37 times 10 to the negative 7 meters. Being a little bit shorter than blue light, this is ultraviolet. But we're actually asked about the frequency, and so we can use that universal wave equation. Solving for frequency means we take 3 times 10 to the 8 meters per second, that speed of light, divide that by 2.37 times 10 to the negative 7 meters. That gets you a frequency of 1.27 times 10 to the 15 hertz. But sometimes we do want to use those electron volts. In this case here, we want to calculate the momentum of a 660 kilo electron volt photon, meaning the energy is 6.60 times 10 to the 5 electron volts. And for calculating momentum, well, we've been given an energy. E is equal to PC, or E over C is equal to the momentum. That energy is 6.60 times 10 to the 5 electron volts over 3 times 10 to the 8 meters per second. That gets you a momentum of 2.2 times 10 to the negative 3 electron volt seconds per meter. Now, if you wanted to convert this into our regular standard units, we've got this in electron volts. Well, it's 1.6 times 10 to the negative 19 joules per electron volt, and the electron volts cancels out, and we'll leave you with an answer of 3.52 times 10 to the negative 22 joule seconds per meter. Now, in either case, this will work. But if you take a look, 2.2 times 10 to the negative 3 electron volt seconds per meter is a much more manageable number then 3.52 times 10 to the negative 22 joules seconds per meter. And so a lot of times you will see things in electron volts, even though it is a non-standard unit, simply because it is more manageable and the conversion rather simple. Okay, I would like you to pause the video at this point. Give this one a try. You're looking for both the wavelength and energy of a photon with a momentum of 6.00 times 10 to the negative 21 kilogram meters per second. Pause the video now. Okay, as you went through this, you should have found that the wavelength was 1.1 times 10 to the negative 13 meters, and the energy is 1.8 times 10 to the negative 12 joules. Okay, so if you are with other people, take time to pause and discuss which one has more momentum, the longer 500 nanometer photon or the shorter 200 nanometer. And please explain your reasoning, but just pause now if you're discuss. Otherwise, think about this and see which one it is before continuing on. Okay, and welcome back. Now, because the energy and momentum are proportional to one another, there is a direct relationship between the two, meaning that more energy equals more momentum. If you double the energy, you will double the momentum that photon has. Now, because, as discussed previously, longer wavelengths have less energy. Therefore, shorter wavelengths have more energy, and therefore the shorter 2.0 nanometer photon will have both more energy and more momentum. So more energy and more momentum. Taking a look at example number 4 here, we're asked what is the wavelength of a 660 kilo electron volt photon. 660, again, kilo electron volts is 6.60 times 10 to the 5 electron volts. And we want to know this wavelength. Well, we do know that energy is equal to momentum times the speed of light, and we know that the momentum is equal to h over wavelength. Now we could do this in two spots, but I'm going to actually just substitute this in and make one equation using hc over wavelength. Again, you could solve for the momentum and then plug it in here, but this seems like a little bit less convoluted way of going through it. Now, because we've got this in electron volts, we can do the non-standard 4.14 times 10 to the negative 15 electron volts seconds for Planck's constant. 3 times 10 to the 8 meters per second. We've got the energy in electron volts, 6.60 times 10 to the 5 electron volts. Notice the electron volts cancels out, the seconds cancels out, and you're left with an answer in meters. And specifically, that is 1.88 times 10 to the negative 12 meters. Okay, and again, we kind of already gave that away at the beginning, that these are X-rays that are typically coming through, and so that would be an X-ray. But what if we wanted to find the momentum with this electron? Well, this is actually a little bit easier. In this case, E is equal to PC, or E over C, is equal to momentum. Now, we could leave this in this this electron volt format, and so you will use 6 times 10 to the 6 electron volts divided by 3 times 10 to the 8 meters per second for momentum, and the momentum you get here is 0.02 electron volt seconds per meter. Again, not a standard unit, but is one that we can use. Okay, if you're wanting to convert this into the standard units, well, the conversion can be direct from this answer that we've got, because 1.6 times 10 to the negative 19 joules per electron volt is our standard conversion. Notice, and you're going to be left with an answer of 3.2 times 10 to the negative 21 joule seconds per meter. Now we're back to standard units. Again, 0.02 electron volt seconds per meter is a little bit more manageable to handle than this 3.2 times 10 to the negative 21. And that's one of the reasons why a lot of times people use the non-standard electron volts for many of these things. Okay, give this one a try. You're going to pause the video and find the wavelength of a 100 kiloelectron volt X-ray. Pause now. Okay, welcome back. And you should have wound up with 1.24 times 10 to the negative 11 meters. Again, that's from combining these two. Now, again, you could have calculated the momentum and then plugged it in here, used two sets of formulas, or you could have combined them, such as done here. But using 4.14 times 10 to the negative 15 multiplied by the speed of light divided by the energy does in fact get you that wavelength. So what about this angle? This formula, this other formula that we haven't really talked about yet, is a little bit different in the fact that it mixes things with wavelengths and electrons. This is the change in wavelength of the photon. So this is dealing specifically with the photon. This m is the mass of the electron, so this is dealing specifically with the electron. H and C standard constants, and so this theta, well, you've got two deflections. You got the electron deflecting and the wavelength deflecting. Which one is it? This theta is actually describing the change in angle of the photon, not the electron. So let's take a look at example 6a here. Wavelength of a photon, 5.00 times 10 to the negative 12 meters, hits an electron at rest. The photon scatters at an angle of 30 degrees. What is the change in the wavelength? So, change in wavelength is equal to h over mc 1 minus cos theta. We're looking for that change in the wavelength. H will stick with standard units of 6.63 times 10 to the negative 34 joule seconds. The mass is our mass of an electron, 9.11 times 10 to the negative 31 kilograms. C is the speed of light at 3 times 10 to the 8 meters per second. 1 minus cos 30. So this change in the wavelength, the numbers in front are 4.246 times 10 to the negative 12, 1 minus cos 30. And it's quite common for students to, somehow this seems to disappear as people go through. Don't forget it. And you wind up with a change in wavelength of 3.25 times 10 to the negative 13 meters. Now that's the change in wavelength. As the photons are coming in, they do deflect off at some angle, passing on some of the energy and momentum to the electron, which means that if this photon is losing energy, or energy is being transferred to the photon, this has to be getting longer. And so the new wavelength, and I know this is not what's being asked, is really taking the old wavelength and adding this amount to it, which is 5.325 times 10 to the negative 12 meters. Now, this is going to be important for example 6b, right? We know that that new wavelength is 5.325 times 10 to the negative 12 meters. Same situation, but we want to know what is the speed of the electron after the collision. We know that photons have momentum, and the law of conservation of momentum is being conserved in this case. And as such, we can actually treat this whole problem as a law of conservation of momentum question. We've got momentum of the photon coming in, h over wavelength, plus the momentum of the electron. We know that's zero, and so that's going to eventually cancel out because it's an electron at rest. The new momentum is going to be using this wavelength, plus the momentum of the electron after the collision. So as we can see here, we can take our 6.63 times 10 to the negative 34 over the wavelength of 5 times 10 to the negative 12 is equal to 6.63 times 10 to the negative 34 again, divided by 5.325 times 10 to the negative 12 plus mv. So before, when you calculate out 1.326 times 10 to the negative 22, I'm going to use Newton seconds there just to keep nice standard units and less writing. Afterwards, we've got 1.245 times 10 to the negative 22 Newton seconds plus mv. Subtracting this from both sides leaves us with 8.09 times 10 to the negative 24 is equal to mv. Well, we're going to divide both sides by that mass of the electron. So 8.09 times 10 to the negative 24, divide that by 9.11 times 10 to the negative 31 kilograms, means that 8.88 times 10 to the 6 meters per second is the velocity of the electron after the collision. And again, all we're doing here is using that law of conservation momentum that we talked about earlier in the course. So key takeaways again. First of all, photons have momentum, even though they're massless. We know that with this formula right here. Photons will collide with electrons and conserve energy. We could have done that previous problem as a law of conservation of momentum. And we can find out that change in wavelength as it gets longer by measuring that angle in which that photon deflects from. Right, this is the angle again of that photon. Okay, Thanks for watching, everyone, and I do hope that helps. Please let me know if you do have any questions.